All right, so we're going to take a deep look into paper one here. What I really want to do is focus on the stuff that you guys have been asking me about a lot through the emails. Okay, so you've been emailing me in about stuff that you're struggling a little bit with. So I'm going to kind of prioritize that. I'm going to focus on that first of all right? And we'll get through as much as we can, okay? But it's really going to be focusing on the stuff that's likely to come up in June, so you can focus your attention on that over the next couple of weeks. Okay, so as I said, I'm going to be on the chat, keeping my eye on the chat for the entire class. If you have any questions, feel free to pop them into the chat, and I'll answer them as we go along. Okay, so just to put this in perspective, what we're going to start out with here, all right? So, thanks, Jay. So what we've got here on the notes that we're going to cover today, you can see we're going to have a look at applications of functions. That'll be your exponential, your logarithmic, and your cubic functions. I'm going to do a trigonometric function with you on Friday when we're looking at paper 2. All right, we're going to have a look at sequence and series. Quite a few of you have asked about sequence and series, so we'll certainly have a look at sequence and series and applications of calculus. So certainly a lot of you have been asking about sequence and series and calculus. Okay, so we'll have a look at those two probably first and get those out of the way. All right, and we'll also then have maybe a quick look at some functions, a little bit on the application of integration, although we'll be doing a lot of integration when we're dealing with the applications of functions, some of the trickier bits in algebra, indices and logs, and then complex numbers and proof by induction, another one that a lot of you guys have been asking about. Okay, so they're the kind of the topics we're going to have a look at. I'll cover as much of it as I can with you this morning and see how we get on. Okay? So, what I'm going to start out, the topic I'm going to do first is I'm going to start out with the sequence and series because that's the one that you guys have been asking most about. So I'm going to start off, if you don't mind, on page 15. Okay, so we'll start off with the question on page 15. Right, it's question number 4, right? Now, sequence and series, remember, this is typically a long question on paper 1. And a few of you have been asking about financial maths. So financial maths, remember, is on the course as an application of sequence and series. All right, that's what that's on the course for. And financial maths has been on the paper the last 2 years running. So I don't think it's going to be asked again. It's not impossible, but I don't think he'll ask financial maths 3 years running. I think that'd be unusual. It's not a topic he's particularly keen on. So I would think that what's a bit more likely this year is we're going to get a long question on either geometric sequences or quadratic ones. So I'm going to take a look at an example of both of those with you here, just to kind of nail that down. Right? At the end of the handout, you'll notice there's a list of recommended exam questions for each of these topics here. So past exam questions you could have a go at. There's 2 that I'd kind of flag for geometric sequences for you. The pendulum question and the antibiotic question. I've kind of listed those for you, 2020 and 2021 at the back of the handout. All right? But this one here we'll take a quick look at. Is the first one is an application of a geometric sequence. Right? So you can see the way it reads. It says the annual yield of a silver mine is the amount of silver produced in a single year. Right? A particular mine has a total yield of 2,420 kilograms in year 1, and the annual yield of the mine decreases year on year in a manner that can be modelled by a geometric sequence. Okay, so being told it's a geometric sequence. And remember, what a geometric sequence is one where you begin with a particular value and you keep multiplying by the same thing to produce the subsequent numbers in the list. In an arithmetic one, you keep adding the same thing. Geometric, you keep multiplying by the same thing, right? And with a common ratio of 0.90. And remember, it's written that way, so it's 0.90. And both the 9 and the 0 have dots, and that means it's 0.90 recurring. That pair of numbers repeats, okay? So that's 0.90, 90, 90, and so on to infinity and beyond. All right, so that's the common ratio. So part 1 says use the sum to infinity of a geometric series to show that 0.90, that this decimal here can be written as 10 over 11. Okay? James, if you go onto if you go onto the download notes tab on the main page of the platform and go down near the bottom, so scroll down towards the bottom, you'll see Leaving Cert Easter notes down there, and the maths ones, it's the paper 1 notes you're looking for. Okay, so it's the download notes tab on the main page is where you'll find those, right? So I'm asked to show that this can be written as 10 over 11. Now, using this sum to infinity formula is something that the examiner, he asked a question like this in 2012, the first year of Project Maths, and hasn't asked it since. Can you use the sum to infinity formula to write this here as a recurring decimal? Now, what's just worth pointing out, kind of just to take a quick detour here for a second, okay? If you just look at the notes on page 92, So if we just go to page 92 of the notes for a second. Okay, just a quick word on this. So down at the very bottom of the handout, page 92, we've got the proofs from paper 1. Okay, so the paper 1 proofs are down here. Sorry about that. Right. So there you can see on page 92, that's the proof of the sum to infinity formula, right? And a lot of people have been asking, certainly in the last couple of weeks and in a couple of the courses I've done so far this week, what proofs should we be doing? So in terms of proofs, what should I be learning off? So we'll talk a little bit about the paper 1 proofs here. I talked about the paper 2 proofs, obviously, on Friday, right? So there are 4 required proofs for paper 1, right? The one you're looking at there on page 92 is one of them, the sum to infinity formula. Okay, so you've got that sum to infinity formula is one of the 4 proofs on paper 1, all right? You can see on the next page in your notes, okay, the next proof is the proof of the amortization formula, right? So you've got the amortization formula proof, and that's quite a long one. It's actually done like a financial maths question, all right? The one below that on the next page, on page 94, is the proof of De Moivre's theorem by induction, right? And the bottom one, the last one then, on page 95, is the proof that root 2 is irrational. Now, they're the 4 required proofs on paper 1. Right? So how many or how few of those should I do? What I would suggest is the number of proofs you do depends on your on what you're looking for grade-wise. If you're looking for a H1, it's not the worst idea in the world to try to familiarise yourself with all of the proofs. Okay, it just means you're going to have your full choice on the paper. It means no matter what he throws on the paper, you're not going to have to leave a question out because it contains something you haven't looked at. So I think it's good practice there if you're looking for the top grade in particular to try and look at them all. If you're looking for something kind of H3, H4 or below, you can actually get away without doing any proofs at all. Because if a question comes up with a proof in there, you can skip the question, or even if you have to take a question with a proof on, because the other questions haven't broken your way, you can afford to take the hit of 5 or 10 marks for the proof if you're not looking for one of the top grades. So if you're looking for kind of H3 and below, you could leave the proofs out altogether. I would suggest that a pretty good middle ground is just to kind of do the most likely proofs. Okay, on both papers. Just do a few of the more likely ones and take your chances. Now, on paper 1, that for me, the sum to infinity one is the most likely of the 4 because it's the only one he hasn't examined yet, and it's only like 3 or 4 lines. So that's one I think I would have a look at, that proof. It's on page 92 of your notes there, so that's one I think I would look at. The other one that I might take a look at is De Moivre's theorem by induction. I think we might get an induction question this year, and any year that induction is possible, he may very well ask the De Moivre's theorem proof, right? That's the one that's on page 94. So page 92 and page 94, I'd prioritise those 2. This one down here is by far the least likely. The proof that root 2 is rational. He's already examined that one twice. So asking that one for a third time when there's one he hasn't tested yet, I think is a little bit unlikely. That'd be way down the bottom of my list. Okay? And then the amortization formula would be down near the bottom as well because I don't think he's going to ask financial maths again. And he wouldn't ask the amortization formula if he's not going to ask financial maths. So I think a nice middle ground between leaving them out completely and doing them all is maybe just have a look at those 2. The one on page 92 and the one on page 94. The sum to infinity formula and De Moivre's theorem. If one of the other 2 comes up, you can take the hit, okay? But I think of the proofs he could ask of one, they're the most likely, and the proofs are there on your notes for you. Okay? Does that make sense? Right. So that's the proofs. The proofs that we're talking about here, and the proof, as I said, is on page 92 for you. Okay. So, what we're going to have a look at then is in this question here. So what we're asked to do is to use that sum to infinity formula, because that's what he could do. He could ask you to prove that formula first, and then maybe use it like this. So the proof formula itself, it's on page 22 of your formula booklet. The sum of infinity is equal to a over 1 minus r. Alright? So in your formula booklet on page 22, that's where the geometric sequence formulas are, and you can see it's down near the bottom here. Okay, there it is. Sum of infinity formula, a over 1 minus r. So the bottom of page 22, that's your sequence and series page. Okay, so down near the bottom there is where the sum to infinity formula is. Right? And remember, the sum to infinity formula, to use that, you need to know what a and or are. A is the first term in your sequence, and or is the number you keep multiplying by. So to use that formula to write a recurring decimal as a fraction, what I need to do is I need to write these decimals here as a series of fractions, which I can add up using the formula, right? Now this is based on the idea of place value. If you have a number like that, say you've got 0.2184 or something like that. Remember this number here, the first number after the decimal point is tenths, it's over 10. So that number there is 2 over 10. And then this 1 here, that's over 100, that's 1 over 100. Okay, and that 8 there is 8 over 1,000 and so on. So the first number after the decimal place is tenths, it's over 10, then over 100, then over 1,000, then over 10,000 and so on, right? So if I wanted to write this here as a series of fractions, I could write as 9 over 10, right, plus 0 over 100, plus 9 over 1,000, plus 0 over 10,000, plus 9 over 100,000, and so on. I'll have a series of fractions that look like that, right? The problem is obviously because in that series of fractions, the number above the line keeps changing. I've got 9, then I've got a 0, then I've got a 9, then I've got a 0. So the number above the line keeps on changing. So because in this question here, the numbers repeat in pairs, I'm going to write the fractions with the number, I'm going to keep the numbers in pairs. So if you see that, I'm going to take those two, so I've got 0 there before the decimal point, that's 0 there, and then I'll take these two numbers, 9 and 0, and put them above the line in a fraction like that, okay? And then, so take these two digits here and put them above the line as well. Take these two here and so on. So it's a series of fractions with 90 above the line. Because the numbers 9 and 0 keep recurring, it's just a series of fractions with 90 above the line each time. The only question now is what numbers go below the line. Right, but that's the idea there. So if you've got a number, if it was just one number repeating, like it was 0.88888, you'd have 8 over and then 8 and 8. Each fraction would have 8 above the line. But when two numbers recur, it's better to keep the two numbers together, because otherwise you'd have a series of fractions where the number above the line keeps changing, and then those fractions don't form a series you can add up with this formula here. So because if I take the numbers in pairs, each fraction is 90 above the line, so this is now a series I'm going to be able to add up using my formula. The question is what number goes below the line. Well, notice that 0 there is that one. And you can see that's the 1, 2, that's the second decimal place, so that means 2 zeros below the line. So because this 0 here is this one, it's the second decimal place, that's 2 zeros, right? This 0 here is that one. So you can see that's 1, 2, 3, that's the fourth decimal place, so that's 4 zeros, right? This 0 here is that one, so that's 1, 2, 3, 4, 5, 6 zeros, that's the sixth decimal place, and so on, right? And then that list of fractions goes on forever. So that's the first thing. If you're asked to write a recurring decimal as a fraction using this formula, that's your first step. Okay? Like that. So now I can add them up using the formula. So remember, when you're dealing with a geometric sequence, to use the formulas here, A is the first term in the sequence. So that's A there. It's the first fraction of this here. So the first term in your sequence is always A. And to find or is the number you keep multiplying by to produce this list of fractions here. To find or, take any number and divide by the one before it, right? So if I divide that number there by that one, so 90 over 10,000 divided by 90 over, you can do that on your calculator, right? And that comes out at 1 over 100. That's or. So to find your value for or, take any number on the list and divide by the one before it. Right? Because you're trying to find what you multiply by, so you divide by the one before to find out what that is. So I'm multiplying by 1 over 100 each time. So there's my value for A, there's my value for or. I just fill them into the formula now. So the sum to infinity is A, which is 90 over 100, the first number in my sequence, all over 1 minus or, 1 minus 1 over 100, and that comes out at 10 over 11. Okay, if you put that into your calculator, it comes out at 10 over 11. And you can see that the entire number just consists of that 0 plus what all these numbers add up to. So 0 plus 10 over 11 is 10 over 11, which is as required. You don't need to write that down, but that's what he asked you to show. He asked you to show that it was equal to 10 over 11, right? So that idea there, so if he does test that sum to infinity formula, all right, if he does test that formula, then he'll probably do it that way. So he'll probably ask you, if he asked you to prove the formula first, he could very easily ask you to do something like this afterwards. Okay, I think maybe that's the reason he hasn't asked that question in a while. All right, because he's saving it in his back pocket for the first time he tests the sum to infinity formula, which he might do this year. So sorry, Michael Joe, does that mean you can't find the maths notes? Are the maths notes not there? Just let me know if you've got a problem finding the maths notes, and maybe get someone to pop up on the news feed for you. Okay, so if you can't find them, the maths notes, I had a look at them there earlier on this morning, and they seem to be there. So if you've got a problem accessing them, let me know. I'll get someone to pop up on the news feed. Right? So that's the first part there. So we've proven that it's 10 over 11. Right? So part 2 then, it says write an expression in n for the annual yield in the nth year. So what this series looks like here, you're going to start out, in the first year you've got 2,420 kilos of silver produced, and then every year the amount goes down because we multiply by 10 over 11. So every year the amount is multiplied by 10 over 11, so it'll get a little bit smaller, right? So to find an expression in n, you're asked to find the general term, Tn. Right? So Vicky asked there, why is 0 not the first term? That's a good question, right? Because you can see that 0, because 0 is when you were dealing with a sequence like this, if the number looked like that, say for example you had 2.1, say 2.11111 like that, right? If I pull that across, part, I'll get 2 plus 1 over 10 plus 1 over 100 plus 1 over 1,000 and so on. Right? And the question is, why is that not the first term in the series? Why would I start here? Right? The problem is that because that's not a fraction with 1 above the line, if I divide this by this, I don't get the same answer as dividing that by that. So those numbers don't form a geometric series. Right? So that number is not like other girls. That number doesn't behave the same way the rest of them do. Right? So dividing that by that does not give me the same answer as dividing that by that. So the numbers don't form a geometric series if I include this one here. So what I've got to do is ignore that one, add that series up using my formula, and then add the 2 separately at the end. Okay, so the same thing with this 0 here. If I divide that by that, obviously I can't divide by 0 anyway, but you can imagine that if the common ratio is 10 over 11, if I multiply 0 by 10 over 11, I just get 0. I won't produce a list of numbers at all. So if there's a number at the beginning here, that number will be separate. It won't be part of your series. Your series will always be a set of fractions with the same number above the line. That's where you can add up, because dividing this by this gives me the same answer as dividing this by this, or this by this, and so on. That's what forms the sequence. Hope that makes sense? That okay? So Vicky, so just the question, why I'm starting here. Okay, so A, that's not A, that's A. Okay, so that's the series I'm adding up here. If there's a number in front here, I'll add that on separately. So in part 2 then, it says to write down an expression, and that's the general term. And where your general term is on page 22. There's your general term formula there. Tn equals A times order of n minus 1. That's the general term for a geometric series, right? That's the formula you're going to use here. So my general term for the sequence is Tn is A or to the power of n minus 1. That will let you jump to any number on the list without having to write down all the ones leading up to it. Right? So what I'm not going to do, if I want to get term number 8, I don't have to work out what term number 2 is, and then work out what term number 3 is, and term number 4. I can jump straight to term number 8 using that formula there, which is on page 22. Just fill in your 2 values. So Tn is equal to A, which is 2420. Okay, times n, which is 10 over 11. Sorry, or, which is 10 over 11. We just found or was 10 over 11 to the power of n minus 1. And now you leave it like that. Do not multiply these two together here. That's a very common error when you're using that formula. Because if you do that, you're doing a multiplication m before you do an exponent e. You're not following BEMDAS. Okay, so when you put your value for a and or in here, you can't go any further, all right, unless you've got a value for n, because you'd have to do the power first before you do the multiplication. Okay? Right. So that's the answer to part 2. There's my Tn formula. And then in part 3 on the next page, on page 16, we just have to use that formula. So it says, hence complete the table below showing the annual yield for the first 5 years. So you can see you've got a table here where you've got the year across the top there. So year 1, year 2, year 3, year 4, and year 5. And you've got the yield below, right? So in year 1, the yield is 2420. And then to get the yield in year 2, you'd multiply that by 10 over 11. Because remember, that's how we get our sequence. All right? So in other words, if I just put n equal to 2 in here, So put anything to 2 in my formula there. If I put anything to 1 in my formula there, 1 minus 1 is 0. So when you want anything to the power of 0 is just 1. This becomes a 1, and you just get that number there. So put anything to 2 in there, okay, to get the yield in year 2, and that's 2,000. Okay, put n equal to 3 in here to get the yield in year 3, and that's 2,200. Okay, put 3 in here, you get 2,000. Right, put n equal to 4 in there, you get 1818.2. And put n equal to 5 in there, you get 1652.9. So those numbers there, that list of numbers there, that's a geometric sequence. Because what I'm doing there to produce each number in that list, I'm taking the one number and I keep multiplying by the same thing. So take that number and multiply by 10 over 11, multiply by 10 over 11, multiply by 10 over 7. That's how you produce a geometric sequence, right? And a long question on this is not an unlikely question this here. Okay? So Katie said there is the common ratio not 0.90. It's 0.90. If you want to use it that way, you'd have to use it as 0.90. Remember, with the recurring symbol on top. So that's what I told you. Okay, it's not 0.90. If you look at the way, read the question, that the common ratio is 0.90 recurring, which we've shown is 10 over 11. That's easier to work with than trying to type that into your calculator every time. Okay, so the whole point of part 1 is to show that the 0.90 you gave me the question is actually a fraction 10 over 11, and that's what I'm going to work with going forward, because that will be very hard to work with when we start solving equations in a moment. Is that okay? Yes, so as I said, Kate, so you're better off writing it as 10 over 11 because it's not wrong to write it that way, to put that in the bracket here, but just if I do, it'll make the equations pretty tricky to solve later on. So you're better off using the fraction you asked to find in part 1. Okay, part 4 then, find the silver yield of the mine in year 21. So obviously we're just kind of jumping forward a bit here, year 21, that's just using the formula again. So T21, okay, then the 21st number in that list, it's just 2420. Times 10 over 11 to the power of 21 minus 1. And if you pop that into your calculator, it comes out at round about 360. Okay, there's no penalty for rounding there because he didn't tell you how to round it. So however you choose to round that is up to you, but make sure you put in your units. Okay, kilograms. I did need to include the units here because kilograms was listed in the table. So he gave me the units in the table here, so I don't need to include them, but I lose a mark if I don't include the kilograms there. So it's a practical question to make sure you include your units. Okay? So it's 360 kilograms there or thereabouts. And then part 5, it says a mine is deemed unproductive when the annual yield falls below 100 kilograms. Find the first year in which this mine will be considered unproductive. So the question is, what year would give us an answer that's less, the first year that would give us an answer that's less than 100? Now, you've got two options here in a question of this type, right? Because if you get a long question in a geometric sequence like this, he'll probably ask this question, or a version of it, right? So what value of n would I have to put in here to get an answer that's less than 100, right? So what I'm going to do is I'm going to solve it as an equation. I'm going to say, look, if I take my general term, so 2420 times 10 over 11 to the power of n minus 1, and put it equal to 100. Don't worry about it says less than 100. So don't make an inequality out of it there because we're going to be using logs, and inequalities don't behave themselves when logs are involved. Just find the value of n for which it's equal to 100 and take the first whole number above that. Okay, so don't worry about inequalities. Just take the first whole number above and go from there. Okay, so what I'm going to solve the equation, I'll divide across by this number first. So I get 10 over 11 to the power of n minus 1 is equal to 100 over 2420. Just divide across by that number first. And now there's an exponential equation. So remember, we've talked a bit about those. We'll see a little bit more on those later on this morning anyway. Remember that an exponential equation, if you're trying to solve this guy here, 3 to the power of x equals 81. To remove 3 to the power of here, we have to use logs. And the opposite of 3 to the power of is log to the base 3. So I go with log to the base 3 on the left-hand side like that. Because these base numbers match, they will cancel and leave the x behind. So whatever I do on the left, I got to do on the right. And what I'm asking when I put this into my calculator, this thing here, I'm asking my calculator how many times do I have to multiply that number by itself to get that one? And your calculator will tell you the answer is 4. Because 3 by 3 by 3 by 3 is 81. So to get rid of a power like this, you use a log, but it has to be log to the base that number. So to get rid of 10 to the power of, I'll use log to the base 10. To get rid of 5 to the power of, I'll use log to the base 5, right? So to get rid of 10 over 11 to the power of, I'll use log to the base 10 over 11. Right? So whatever the number you're raising to a power here is, log to the base that number will remove it. Right? To the power of n minus 1 like that. So because these base numbers match, they are opposites, they will cancel and just leave the n minus 1 behind. So whatever I do on the right, the left I got to do on the right. So I'll pop that into my calculator now. Log to the base 10 over 11 of 100 over 2420. Right? And if I pop that into my calculator, I'm going to come out with an answer that's about 33.4. Okay, so we move the 1 across, we get n is 34.4. So remember that n can't be a decimal here. When you're dealing with geometric sequences, you can't have the 34.4th number on the list. Okay, so we take the first number above that, so it's the 35th number, so n is 35. Okay, so once he's the number 35, year 35 is the first year when the yield will drop below 100. Now, that's a tricky equation to solve, particularly if you're not comfortable with using the logs here. So what you can do instead for full marks is you can Goldilocks it. So suppose I take this from here, I just start dropping in numbers there until I find the first one that gives me an answer that's less than 100. It's called Goldilocks because what you'll probably do is you'll probably find a number that gives you an answer that's bigger than 100, and then one that gives you an answer that's a lot smaller than 100, so the correct one's somewhere in between. So maybe if I try 20, I'm still above 100. Okay, I try 30, I'm still above 100. I try 40, I'm well below 100. So somewhere in between those two is the one I'm looking for. I can zone it that way. And if you do it that way, you will get full marks. It's not quite as random as it sounds, but to get there directly, you do it this way. But remember that because the equation, the formula is quite tricky to work with, the most important thing here is I get full marks. So if I can't solve the equation or I get bogged down in that, get your calculator out and just start trying to find a value, the first value, that when you put it in there gives you an answer that's less than 100. Right? So if you do that, I mean, if you try, for example, if you try the number 34 in here, if I put the number 34 in here, I get 104.2. That's still bigger than 100. If I try the number 35 in here, I get 94.7. So 35 is the first number, which when I drop it in here, gives me a yield that's less than 100. So that's where I get my answer. So they're your options when you're dealing with a geometric sequence like this. Okay? But the answer there is n equals 35. I hope that's okay. Now, part 6 then on the next